Good morning, everyone, and welcome live to the Oxford University Museum of Natural History for the first session of the 2020 virtual annual meeting of the Palaeontological Association. You are all very welcome. I can see you joining us in the chat from all around the world. Thank you for joining us so early in the morning, or it might be so very late in the evening, depending on where you're joining us from. To start with, we've got a few announcements before we get to the first talk at 9:15 UK time. So we're going to start off with a few technical announcements on how this presentation system will be working this week, and then just a few reminders about some of the events and how you can be involved. So, just a reminder that if you have any connection issues this week with this webinar jam system, there is a reconnect button at the top of the page. We're not expecting any problems, but if you do have problems, do click that reconnect button and it will re-establish your connection with the webinar jam servers. Now, we want your questions to be coming in to our speakers, and the best way to do that is in the chat. I can see you all typing away there. So if you've got any questions for our speakers, do pop them in the chat as you think of them, and then our chairs can be collating those questions. And if you can mark that they are a question by clicking the small circle to the right-hand side, that will make sure we set them out from your wonderful introductions from around the world, and the chairs will be able to bring those all together. Now, I am just going to hop across and call up some slides so that we can see. Here we go. So just a few reminders about how things will be working this week. I'd want to remind everyone about the association's code of conduct that is available on the website, and as delegates to this meeting, you have all agreed to abide by that. Should you become aware of any breach of the code of conduct, I would encourage you and any other people who have witnessed that to report it on the new online reporting form, which can be found on the events section of the website, on the PALAS 2020 meeting section of the website. These meetings don't happen by themselves, and I would just like to say a huge thank you to the organising committee, who have been such an integral part of putting together the plans for this week and indeed executing the plans for this week. And I'm also very grateful to the scientific committee, who have played a huge role in reviewing all your abstracts and making the decisions there. There's two other people who are not on this list who very much deserve your thanks, and all members of the association and attendees at this meeting should know what a huge role they play in these meetings. The first is Joe Hellawell, who is the executive officer of the association. Those who are in the know about how things work within the association know nothing happens without Joe's help and support. She is a hugely integral part of the association, and we all owe her our thanks. The other person is Russell Garwood. He is a coroller of the digital data flowing seamlessly around the world, and is the man behind the website. The annual meeting simply could not happen without his help and support, and we all owe him a great deal of thanks. So if you see Russell about in the digital world, or hopefully in the future in the real world, do say hello and a thank you for all he does for our association. Now, just a reminder about the three presentation formats we're going to be seeing this week. On this webinar jam system, we're going to be having the talks. So you're going to be seeing standard talks, as we're seeing in this session now, up to 15 minutes, hopefully 12 minutes, so that there's 3 minutes for questions. We're also going to have some flash talk sessions. So these will be talks of no more than 5 minutes. And then at the end of the session, we will have a Q&A panel when you can both put your questions to any of the speakers, and the speakers can comment on each other's talks as well. We've tried to group them together, with themes, so that will really get some more debate going. And just a reminder, in case there are any speakers watching, please do remember to use your speaker link when you are accessing to give your presentation. You will not be able to use your attendee link to give your presentation. And a reminder to all presenters, please stick to time. It is so important in an online meeting that we keep to time. So our chairs have been instructed to be, quote, ruthless with the clock. So please, everyone, do stick to time. Now, just a reminder, we are also using a Discord server. All delegates will have received an email in their inbox about how to access the Discord server. If you've been having troubles getting your emails, do check that these emails aren't going into your spam or promotions inbox. Discord, as well as hosting the poster sessions, we have one later today and another tomorrow, will also host a number of meeting rooms which delegates can use at any time, and a number of other channels where you can hang out and have a chat about various topics. I'd also remind people that later today there's an LGBTQ+ meetup on Discord, and there's instructions on the Discord channel about how to join that meetup, because you will need permission to join that. And we're also very pleased to be joined by Rachel Erin Illustrations this week, our in-house illustrator, who's going to be drawing her way through Pallas and will be posting her wonderful drawings on a special channel on the Discord server. Later today, we'll be having our annual meeting symposium, and I'm very pleased we're going to be welcoming these fine speakers from all around the world to speak to us about we really cover the entire geological column with these speakers. Sadly, Rahab, for family reasons, can't join us today. I've sent our best to Rahab and her family, but sadly, that means we will be finishing 30 minutes early this evening at 5 p.m. London time. And a reminder that tomorrow at 7 p.m, we are joined by Professor Rachel Wood from the University of Edinburgh, who will be giving this year's annual association address on the topic of Tales from the Cambrian explosion. It is definitely going to be a treat, having seen Rachel give a talk via our system earlier in the year. I know it's going to be wonderful. That is open to the public. You should have all received information about this in your delegate packs. But if you know anyone who might be interested in joining us for that, it's going to be a very accessible event. So do go on the website where the details are on the annual meeting page, and you can share those so others can join us. And each lunchtime, UK time, we're going to be having a mini field trip using some of the wonderful collections we have here at the museum. This isn't some fancy Zoom background. This really is Mesozoic limestone that the museum is constructed of. We are actually here and we want to show you some of our wonderful collections. So today, we're going to be finding about the first fossil field guide from Edward Hewitt. So join me and Hilary Ketchum, one of our collections managers, who's going to be showing us all the way through that. And then tomorrow we have Mary Anning and Elizabeth Philpott, and then Megalosaurus on Friday. So do join us. Links for that are in your delegate packs. And then on Friday evening, I will be joined by my dear friend and colleague, Duncan Murdoch, for the Paleovision Fossil Contest. A bit of fun to wrap up the week. So do join us for that. Again, information is in your delegate pack. Now, at that point, we can see that our speakers are hiding behind their numbers. Here's a bit of, while we're just waiting for 1:15, we're going to play a short video in a moment, but I will set a little challenge and we'll see if anyone can get it, and maybe put your answers in the Discord server so we can keep getting through the link. There will be the prize of some pride if anyone can get this. What is the link between the graphics of the numbers that our speakers are hiding behind this week. Just before we get started with our very first talk at 1:15, we are just going to see a quick video from one of our sponsors. Take it away, Richie.
Okay. Oh, hang on, my camera's gone off. My connection seems low at the moment. Okay, sorry about that. My camera won't work for some reason, but I will continue talking anyway. Okay, good morning, everyone. Thanks for getting up so early to this first Palace session. I'm delighted to be talking today about a fossil worm from the Early Cambrian Xianguang biota of Yunnan province in southwestern China, which, if you're not already familiar with it, it's a Burgess Shale type fossil Lagerstätte with soft tissue preservation and a diverse bilaterian animal fauna. And I want to talk about how this worm can help us understand the evolutionary origin of one of the most diverse and abundant clades of organisms on Earth, the Ecdysozoa. So, the Ecdysozoa, these are a lineage of bilaterian animals. So it's one of these three bilaterian animal superphyla, and they are characterized by having a tough chitinous cuticle that must be molted periodically in order to allow the animal to grow. And this includes the most abundant and diverse animals on Earth, the nematode roundworms, and of course, the arthropods. But altogether, we recognize 8 phyla of ecdysozoans, and they are resolved in 3 morphological groups: the panarthropods, here on the slide in green, the nematoids on the slide in blue, and the scaledophorans on the slide in orange. Oh, my video is back, so that's nice. Moving on. So, the fossil record of Ecdysozoa is exceptionally good in the Cambrian period. For some groups, especially the arthropods, we have a genuinely unparalleled phylogenetic resolution of the stem groups of animal phyla and subphyla within the Cambrian biotas in the form of very well-known fossils like lobopodians, radiodonts, megachirons, bivalved arthropods, and others. But we also have this other large assemblage of diverse vermiform taxa, vermiform ecdysozoans, so worm-shaped ecdysozoans with no segmental body plan and paired appendages. But these taxa are mostly poorly constrained in a phylogenetic context beyond their proximity to the priapulan crown group. So some of the most well-known examples of these kind of taxa are things like Palaeoscelicids, which actually range into the Silurian. And also your classic archaeopriapulid type taxa, things like Atoya from the Burgess Shale. So, with such vast diversity in mind, both extant and in the Cambrian, it's been very difficult to ascertain which taxa might comprise the stem lineage of Ecdysozoa, and allow us to reconstruct the origins of Ecdysozoa in a morphological and ecological context. One group that is thought to be key is the Palaeoscelicids. These are elongated, armored worms with distinct cuticle texture, terminal posterior hooks, and an anterior spiny proboscis. There's an example here on the left, Marfangscolic sinensis, which was redescribed by Yang et al. Earlier this year. Now, these kind of worms have been discussed in the context of Ecdysozoan origin several times, with some studies supporting this and some studies doubting this. But the problem is that this group is almost certainly a polyphyletic assemblage, and therefore their systematics needs to be thoroughly revised in order to improve their phylogenetic informativeness. Essentially, they likely form the stem groups of more than one taxa. So, with these problems in mind, this is where our worm enters the equation. Its name is Acosmia mautiania. It was described as a priapulin by Chen and Zhu in the 1997 book, The Biology of the Xianguang Fauna. It's a somewhat featureless in some ways worm. It's about 3 to 8 centimeters long, kind of short and fat, with an anterior terminal mouth, a posterior terminal anus, a through gut, a muscular pharynx, and perhaps most distinctively, this annulated, papillated, warty cuticle that is very much like a priapulin. But its status as a priapulin has been in doubt in each subsequent faunal compilation of the Xianguang fossils. So we were interested in taking another look at this rare but interesting worm. So the previous interpretation, as I said, was a priapulin. So that's the phylum Priapulidae, the penis worms. It's represented, which are represented today by about 20 odd species of marine taxa, ranging from macrofaunal to myofaunal. But anyone who's familiar with Cambrian faunas will know that the priapulins were much more abundant and diverse in the Cambrian period. And this contrast has made them quite intriguing to paleobiologists for some time, and priapulins have been the focus of some quite classic and pioneering studies of fossil morphospace occupation, for example. So, with all that interest, it's perhaps not surprising that Acosmia was considered to be a priapulin at the time, as it is often used as a bit of a wastebasket taxon for Cambrian worms. But priapulins do have some very distinctive and fossilizable character that we don't see in Acosmia, mainly these two sclerotized fields of radially orientated armature lining the pharynx and surrounding the mouth. And here's some examples. You can't quite see because my video is in the way. I'll just turn my video off for a second. The bottom right-hand corner of the slide, some SEM images of the pharyngeal teeth and circumoral scalids of the living priapulin Priapulus. You can see a picture of Priapulus above there. I'll turn my video back on now. So here is a comparison of the anterior ends of Acosmia on the left-hand side, and two other examples of Ecdysozoan worms from the Xianguang biota. We have Sisiophorus raris in the middle here, which is a stem group or possibly crown group priapulin. And on the right-hand side, we have Cricocosmia jiningensis, which is likely a stem group panarthropod and has many characters shared with lobopodians. So just looking at these photos, it's clear, especially compared to Sisiophorus, that there are similarities in the gross overall morphology, the bulbous shape of the proboscis and the terminal anterior position of the mouth. But it's clear that Acosmia, and this one shown on the left is the best preserved example, is missing these two distinct fields of radially oriented armature and are labeled in the other worms. Now, these are really phylogenetically significant characters that are missing, the teeth and the scalids, because we have reason to believe from Cambrian Ecdysozoan fossils across the Ecdysozoan tree of life that these two kinds of radial armature lining the pharynx and surrounding the mouth might not just be characteristic of priapulins, they could actually be ancestral characters for the Ecdysozoans, or at least for the Ecdysozoan crown group. Now, the reason for that inference is that several paleontological studies over the last decade or so have reported these fields of sclerotized radial armature surrounding the mouth and lining the pharynx in a range of Ecdysozoan taxa, including panarthropods, like, for example, the Cambrian stem group Onychophoran hallucigenia sparsa from the Middle Cambrian Burgess Shale, in this paper by Smith and Caron, 2015. And they have this really nice cladogram here on the left-hand side of the slide that was included in that paper, showing these reconstructions of these fields of sclerotized radial armature across the Ecdysozoan tree of life, with priapulins at the bottom going up from different panarthropod groups, the Onychophorans, tardigrades, gilled lobopodians, radiodonts, and a living arthropod. So it's becoming clear, possibly, this kind of armament may not just be characteristic of priapulans, it could actually be an Ecdysozoan plesiomorphy, an ancestral character. And there are plenty of other examples. Here's another one from the Early Cambrian Sirius Passet Logostata of northern Greenland, in another stem group arthropod, Pamdelurian. So all this kind of begs the question. Acosmia seems to have these several Ecdysozoan characteristics that we discussed earlier, but it lacks these two fields of radial armature that are possessed by other groups. And this begs the question, is Acosmia perhaps a less derived Ecdysozoan worm? Could this be an Ecdysozoan that sits outside of the crown group of Ecdysozoa? But as I'm sure many people will have caught on, there's a real problem inherent with viewing a fossil that is missing certain derived characteristics as a primitive member of that group. And this is because the fossil record is biased towards the preservation of the most robust morphological elements of organisms, which may not necessarily be the phylogenetically informative characters. So we had a real issue to address when trying to code Acosmia into a phylogenetic matrix. Should these characters that seem to be absent be coded as question marks, unknowns, or should they be treated as objective absences, zeros, which is going to have a much greater effect on the phylogenetic topology? Fortunately, however, two studies have already attempted to quantify the decay bias in Ecdysozoa in soft-bodied Ecdysozoan taxa. One example by Murdoch et al. Using velvet worms, and another one by Stanton using priapulans, which is ideal for the fossil we're considering the previous interpretation of this fossil is as a priapulan. So in these two tables on the screen, essentially you have a ranking of which morphological characters persist into the decay process of these animals for the longest. And in both cases, it is by far the cuticular elements of the anatomy that are the most recalcitrant, the most durable. Fortunately for Ecdysozoan systematists, the cuticular anatomy, things like spines, teeth, claws, cuticle texture, these actually form the bulk of the characters that we use to build Ecdysozoan phylogenies from Cambrian fossils. Therefore, stemwood slippage is not thought to be a major concern for Ecdysozoans as it is for chordates, for example. So on the right-hand side here, we have photos of the morphology of a priapulan at various stages of the decay process. And Sanson concluded from this study that the most robust elements of the morphology were the trunk annuli and the trunk papillae, which we see in Acosmia, but also the pharyngeal teeth and the scalids, or the circumoral armature, all of which were still present after 224 days of decay. So from that, we concluded that it's reasonable to assume that scalids and pharyngeal teeth are actually absent in Acosmia. They cannot be coded as zeros in this matrix, and the reason being that the trunk papillae and the annulations are present in all specimens we were able to examine, and these tissues were determined by Sanson to be just as durable or almost as durable. So with that in mind, we performed our phylogenetic analyses to determine the position of Acosmia. We sampled 185 characters across 62 taxa, 62 protostome taxa. We started from the protostome phylogeny of Vinther and Parry, 2019 current biology as a starting point, and then subsequently added Ecdysozoan characters and taxa to give us coverage across the major lineages, sampling panarthropods from the Lobopodian papers of Smith, Caron, Ortega-Hernández, and Wills et al. For priapulans and splenuralians. We inferred topologies using 4 alternative optimality criteria. We did parsimony methods, equal and implied weights, and probabilistic methods, maximum likelihood and Bayesian inference. And in each case, we recovered Acosmia as the sister group to all other Ecdysozoans. Therefore, Acosmia is resolved in the stem group of Ecdysozoa, with high support from the probabilistic methods. So, with the position of Acosmia resolved as stem group Ecdysozoa, we decided it would be useful to empirically test which characters inferred to be ancestral for crown group Ecdysozoans from the literature, which of these characters hold up as ancestral characters with the position and character states of Acosmia as a constraint. We did this in a Bayesian context in Mr. Bayes using the MK model, analogous to basic principles of Jukes Cantor 69, so equal probability of character state transitions in all directions. Whether that's realistic or not, it's the best we have at the moment. And these characters that we chose were the anterior terminal mouth, radial pharyngeal armature, radial circumoral structures, the annulated trunk, the scaled covered introvert that we see in many worms, and the paired lateral sclerites that we see in things like Cricotomia. And we did this using 2 alternative phylogenetic hypotheses to control for that uncertainty. And this reflects the contrast between morphological and molecular trees of Ecdysozoa. But regardless of the topology, we got similar results. Terminal anterior mouths and annulated trunks are ancestral for the Ecdysozoan total group, whereas pharyngeal teeth and circumoral structures are apomorphies of the crown group. And this, I think, all sounds simple enough considering the fossils and data we've explored today. But we thought it was important to get real numerical support for these ideas that have been formulating in the literature over the last 10 years or so. So with all that in mind, we can map these characters nicely onto the Ecdysozoan tree and start to speculate in the future, hopefully, what these character acquisitions might represent. Unfortunately, I don't have time now to talk about each one of these characters and their transformations across the Ecdysozoan tree, but there's plenty of discussion on that in our paper, which is out now in BMC Evolutionary Biology. So with that in mind, I will leave it here. So Acosmia is a stem group Ecdysozoan, not a priapulin. We consider from our ancestral state reconstructions that the common ancestor of the Ecdysozoan crown group probably acquired teeth and sclerotized circumoral elements, and we therefore hypothesize that this might have been associated with a shift in behavior or feeding style, for example, a shift to predation. And this might have characterized the diversification of crown group Ecdysozoans. Further things we'd like to look at include the homology of the diverse mouth and pharynx morphological elements. There's a lot of shape and variation in these, and how reliable their morphology isn't clear. And also we'd like to take another look at whether the position of Palaeoscalesis fits into things. So I'll just leave it there. I'll thank my supervisors, my PhD supervisors, Xiaoya and Gregory Edgecombe, as well as Xianguang and Xiaomei at YKLP. And this work was funded by NERC, the NHM, Yunnan University, and Exeter University. Thank you very much, everyone.
Thank you, Richard. We've got 30 seconds for a very quick question from William Foster. What was the ecology of a Acosmia-like worm?
So we don't have that many. We don't have that much material, and they're never in a particularly interesting context for explaining that kind of question. But one idea that was floated in the original description is that because they're often preserved in a kind of U shape, that they might be deposit feeders analogous to a lugworm. I don't really buy that personally because we have so few specimens and the sedimentary context has never been well characterized. But considering it lacks any kind of sclerotized armament, it's probably unlikely that it was capturing prey in the way that you might imagine a priapulin to. So our estimate is probably a deposit feeder.
Excellent. Thank you very much, Richard. There's a number of other questions that have just popped up in the chat, but if you'd like to answer those in the chat during the next talk, thank you once more to Richard. Our next talk is by Sarah Losso and Javier. Unfortunately, Sarah can't be with us today, but has submitted a recorded talk in advance, so we're going to play that.
Good morning. I am a PhD candidate working with Javier Ortega-Hernández on early euarthropod evolution, and today I will be sharing a part of my dissertation looking at Olenoides serratus, which is a trilobite from the Middle Cambrian known from both the British Columbia and Pennsylvania. What is most interesting about Olenoides is that it has preserved non-biomineralized tissues in the specimens found from the Burgess Shale. So here we can see appendages on both sides of the body. Olenoides serratus was the subject of extensive work by Harry Whittington in the late 1970s and early 80s, where he described the appendages as being fairly standard for trilobites. We can see the flagelliform antennae in pink at the front of the body, followed by a homonymous series of biramous appendages. With the endopod or walking leg in purple, the exopod or gill in yellow, which both connect to the protopodite in green, which would then connect to the body wall. Olenoides serratus is unique among trilobites for having another type of appendage. It has these blue cerci at the back of the body, which are not seen in any other species of trilobites. So it has a higher degree of limb specialization than seen in other trilobites. But when we look at that homonymous series of biramous appendages, they all pretty much look the same, and Harry Whittington reconstructed them as just being smaller at the back, but the same morphology. Recent work, such as that by James Holmes, has shown that other trilobites, such as Rhodlichia, have some degree of anterior-posterior limb specialization. So here we can see that the cephalic appendages have proportionally larger protopodites with larger gnathobases and smaller exopods, so they're more adapted to processing food than the posterior thoracic appendages, which have proportionally larger exopods. So trilobites do have some degree of limb specialization. What I would like to focus on today is this specimen from the Royal Ontario Museum, which we can see is broken. It is missing the majority of the cephalon as well as the entire right pleurae. Because the pleurae is missing, we can actually see the appendages on the right side of the body though, so it works in our favor. We can see 3 exopods, all of which are broken. On the right side of the body, we can see 8 endopods, 4 of which are clumped together at the back, making it difficult to distinguish them. We see 1 endopod from the left side of the body, as well as the cerci, which are slightly removed from the body. But what is interesting about this specimen is that 2 of those endopods at the back of the thorax and the front of the pygidium appear to be half the size of the others. So these are only half the length and half the width of the other appendages, including the appendages behind them. At first, this might seem like maybe it's just that they were broken, because we see a lot of other broken appendages here. But those are very easy to identify with their jagged borders. And here we don't see any cracks or breaks along the appendages. They have a smooth dorsal outline, unlike the other broken appendages. So they're not broken on the dorsal side. On the ventral side, we see endites protruding from the distal edges of each podomere, which closely resemble the endites from the other normal endopods. So it's not broken on the ventral side either. We can also see the individual podomere boundaries. And in the anterior, more reduced appendage, we see 6 podomeres, so it's only missing the terminal claws, whereas the posterior, more reduced appendage is slightly more incomplete because it only has 4 podomeres shown. So these appendages are not artifacts, they are reflecting the true morphology, which appears to be quite different than the normal appendages. To investigate the morphology more easily, here are just the outlines of the protopodite and the individual podomeres for those 2 reduced appendages to the same scale. So you can see the 1 centimeter scale up in the right-hand corner. And we can see that the protopodite is in both of them large and subcircular without any endites. The first podomere has this unique W shape on the ventral side with a distal endite. And the other podomeres are square to rectangular with distal endites. We can compare that to an more anterior appendage from the same specimen and see the dramatic differences. So the protopodite doesn't have spines on the 2 reduced, and the first podomere has some pretty distinct differences, especially in endites and the curve shape of the ventral side. These appendages can also be compared to the same appendages from the same position on other specimens, and we see that pattern holding true of the differences in the protopodite shape, where they are more subtriangular, and the distal podomeres of the normal endopods becoming hourglass shaped, and that the endites are in different positions. And this pattern holds true with any of the specimens I compared it to, and even when I compare these appendages to the smallest appendages I can find, so at the back of the body. So although this appendage shown on the bottom is not significantly larger, it has the same morphology as the normal appendages with rectangular to hourglass shaped podomeres at the distal end, which we do not see in these 2 reduced endopods. So what we have is a halaspid Olenoides with two endopods that are greatly reduced with unique morphologies, but the exopod associated with them appears to be a normal length and width. So the next question then is, well, what are these? One interpretation is that they might be limbs that are regenerating after being damaged. Regeneration of appendages is common throughout arthropods, and regeneration of the dorsoexoskeleton is well documented in trilobites. Here is a limb series after damage from crickets, and what is most relevant is the femoral amputation on the right, where you can see that the entire appendage will be released with the correct number of podomeres, and they will then grow with molts to become the correct size and shape. So it is possible we are looking at two endopods that were damaged and are being regenerated and are pretty early on in the regenerating process because they are notably smaller. This would also explain the rarity of this, because you would have to have an individual that is regenerating appendages, it's in the early stages, and it has to be killed, it has to be preserved, and we have to find it. So it would not be expected to see, we wouldn't expect to see that often. And this would be the first known instance of regenerating appendages in trilobites. However, when we look back at this specimen, there are a couple things that are hard to reconcile with this interpretation, such as the protopodite morphology with the lack of endites and the shape difference being more subcircular. And although trilobites do regenerate their dorsoexoskeleton, it follows a developmental pattern. So the oldest tergites, which are in the pygidium at the front of the pygidium, they regenerate first, and then the posterior ones will regenerate. And we would expect to see that with the appendages, but we don't. Another possible interpretation is that these might be specialized for reproduction. Many kinds of arthropods have, in the adult males, one or two sets of appendages will be specialized either for transferring the spermatophore or for holding on to a female. Here I'm showing myriapods where two appendages are specialized as gonopods to transfer the spermatophore to the female. In brachiopods, here at the front of the body are the claspers, which are used to hold on. And again, these are found in adult males. So you would expect to not see them in a lot of the specimens because one has to be an adult and it has to be male. So we would expect to see this in one of the larger specimens. And here, if we look at the thoracic length over the pygidial length with holaspids in light blue and meraspids in dark blue, we see a nice linear trend, and that specimen of interest is actually on the larger side. It's not the largest, but very few of the larger specimens actually have appendages preserved, and there's not a lot of them that are larger. So this is potentially a adult male trilobite, and these could be specialized either for holding onto a female or for transferring the spermatophore. And this would be the first time we can easily identify the sex of a trilobite and the first evidence of significant limb specialization. So to sum up, I presented a single large specimen with reduced endopods at the posterior of the thorax. Unfortunately, appendages are only preserved on one side of the body, but we can see the protopodite is subcircular and lacks endites. The podomeres are short to square or rectangular, and the exopod is normal shape. The first interpretation that these might be regenerating appendages is supported by the size and the shapes, and it accounts for the rarity of why we only see one specimen with this. However, it's hard to interpret some things like the protopodite morphology and the similar size of the endopods as being regenerating appendages. The other interpretation that these might be specialized for reproduction is supported by it being a fairly large specimen, the similar size of the endopods, the protopodite morphology, and the morphology of the podomeres, which is very different than that of the normal appendages. This also would account for the rarity, but with the limitations of the specimen, it's hard to rule out either because we only have appendages from one side of the body. As such, this is the subject of continuing work. I would like to thank both my department, OEB, and the MCZ for funding, Jean-Bernard Caron, Mark Florence, and Doug Irwin for facilitating access to specimens, my lab mates, especially Steve and Joe, for lots of discussion about this project, and my wonderful advisor, Javier, because he is immensely helpful. Please let me know. You can contact me at my email there. Let me know if you have any comments or questions about this project, and I would be happy to discuss it more.
Thank you to Sarah there for her presentation. And as she said, her email is in the chat, so you can contact her if you have any questions. And co-author Javier is also in the audience. So if you want to pop any questions in the chat for Sarah, Javier is happy to pass those on and make sure you get an answer. With that, we will zoom on to the next presentation. And I will just remind people, if you do have questions, ask them as you think of them. And that way we can make sure that more of them get to our speakers. And we're very pleased. We're zooming up to North Greenland. And we're pleased to be joined by Elise Wallet. How are you today?
I'm good, thank you.
Brilliant. And then we will call up your slides and take it away.
Hi everyone, and thank you for joining this session. I'm going to talk about my work that I've done during my first half of my PhD. And this small carbonaceous fossil biota has actually been trapped in rock samples which have stayed in the shelf for decades before they have been finally investigated by our team at Uppsala University, which includes me, Elise Wallet, and Ben Slater, Sebastian, Willman, and John Peel, who actually collected those samples in Greenland in the 70s and the 90s. So as many of you know, Burgess Shale type Lagerstätten are of crucial significance for Cambrian research because they capture whole communities of soft-bodied metazoans in their environments. And so if you want to understand the development of metazoan-dominated ecosystems, then we need to rely on these instances of exceptional preservation. However, as many of you know, these Lagerstätten are very rare. They're restricted both in time and space, as you can see on this map and on this stratigraphic scale. So it's a bit difficult to figure out what's the broad picture behind those little snapshots of diversity. However, relatively recently, some of these Lagerstätten have been expanded. And what these slightly expanded views of Cambrian ecosystems have revealed is a remarkable degree of patchiness in the distribution of fossil biotas. So just as an example, around the Burgess Shale, there has been 2 new localities which have been discovered about 40 kilometers south of the Walcott Quarry. And the biota that they yielded is substantially different from the famous Burgess Shale from the Walcott Quarry, especially one of these sites yielded more than 20% new species. So there are significant lateral variations in community composition, even at a very small scale, and that's also been evidenced to some extent in Xianguang. However, similar variations are not known from the Sirius Placid Lagerstätte of North Greenland, which is another very significant Burgess Shale type Lagerstätte, not least because of its age. It's one of the oldest, and it's also arguably the most remote of the Lagerstätten. So the Sirius Placid Lagerstätte is basically restricted to a kilometer-long outcrop, so it's kind of hard to figure out what kinds of patterns we might find in there. However, relatively recently, about 2 years ago, Ben Slater and others have discovered a new biota of soft-bodied metazoans preserved as small carbonaceous fossils about 200 kilometers south of Sirius Placid. And this biota is significant because it includes the earliest trilobite recovered to date, but also it documented for the first time in North Greenland the occurrence of soft part preservation in relatively shallow shelf environments where conventional preservation of whole body fossils of soft body metazoans is not possible. So the idea with this study was to try and figure out what kind of biotas inhabit those kind of shelf environments and how much this biota differs from the serious basset biota, which was deposited under deeper conditions. So to do this, we used a few samples from 2 different horizons, which were attributed to later stage 4 to earliest, later stage 3, sorry, to earliest stage 4. So we are slightly younger than the serious basset Lagerstätte. And this is a schematical representation of our biota, which mainly consists of arthropods, but there was also a background material of unknown or uncertain metazoans, as well as some scalidophoran scalids. But by far, I would say our most significant find was crustaceans, which were preserved as 3 different types of sclerites, the filter plates, potential laborer, and molars. And as you can see, the quality of preservation is excellent. You can see these very fine rows of statules in these settle arrays, as well as these very finely denticulate molar surfaces. So these are phylogenetically significant characters that definitely identifies them as crustaceans. And apparently, these are the oldest crustacean remains ever recorded to date. The earliest, oldest assemblage of this type has been recovered from the Mount Cap Formation of Canada, but this assemblage is slightly younger than our specimens, which were recovered from the uppermost part of the Nevada zone. So, regardless of their exact age, we are very early in the evolution of the crustacean lineage, and already at this stage we can evidence quite a high degree of differentiation in crustacean appendages with filtering as well as ringing elements. But we've also found quite a lot of remains from bivalve arthropods, which include those spinose and reticulated cuticular fragments, which have been recovered previously in the previous study by Ben Slater and others. And these sclerites have been compared to the bradoid taxon Spinospitella coronata from South Australia. But what was intriguing with those cuticles is that they were preserved in 3 dimensions. They were really stiff, so it allowed us to investigate them further using the scanning electron microscope. And this is what we found. These SCFs are virtually identical to similar fragments which have been found in the type locality of Spinospitella coronata. And moreover, we can see on some of these spines very faint rows of smaller spines, which is a diagnostic feature of Spinospitella coronata. And these distinct cuticular fragments occur also with 3-dimensional spines, which were found in isolation. And some of these spines were also associated with an entire bradoid valve, which preserved this finely reticulated ornamentation. So here we think that all of these different sclerites probably belong to the same species, and this species was most likely to be Spinospitella coronata. But we also found potential other species in our assemblage of bivalve arthropods, including potential remains of Petriana fulminata and their finely granulose ornamentation, as well as some spines from the bivalve arthropod taxon Isopsis, which again have been identified previously based on this faint median fold line, which you can see pointed by the arrow. We've also recovered a few remains from trilobites, which again have been identified in the previous study and compared to Olenoides trilobites, and the particularly relevant candidate here is Limniphacos perspiculum, which occurs as a macrofossil in the same levels. We found also a few scalidopherans, including those typical conical spines, which again have been found previously and compared to priapulid-like scalids, which were born on the trunk and introverted regions of the priapulid-like worm. But we've found a larger diversity of scalids, including these hook-shaped types, as well as completely new morphologies of priapulid-like teeth, which occurred on the pharynx of the priapulid-like worm. And finally, we've recovered a tremendous diversity of beautifully unknown metazoan sclerites, which, in spite of their ambiguity, still demonstrate that a lot of different tissue types can be captured by this mode of preservation. So beyond the serious basset Lagerstätte, we have identified quite a diverse SCF biota, which, as many Burgess Shale type Lagerstätten, consists mainly of arthropods. But our arthropod biota substantially differs from typical arthropod biotas from Burgess Shale type deposits, especially because it contains crustaceans. Crustaceans are not known from Sirius placets, and in fact, crown group crustaceans are not known from any Burgess Shale type deposit. So, and they are the earliest known to date. So this is quite a significant find. Also, we have quite a diverse assemblage of bivalve arthropods, which include the taxon Isoxys. So Isoxys is quite a typical component of Burgess Shale type deposits. It has a widespread distribution. It's also present in Sirius placets as well. And we document it in the shallower water parts of North Greenland. So this is perfectly in line with its inferred pelagic lifestyle. However, the bradyrhid taxa are not known from Sirius placets, and they are not known from any Burgess Shale type deposits. They have a much more patchy distribution, and in North Greenland, they are restricted to shallow water environments. So the big question is the biota that we've just identified, which consists of the earliest crustaceans, the earliest pterobrans, and also bradorids, is this biota bound to shelf environments and dependent on high oxygen levels? And if this is the case, then our current record of Burgess Shale type biotas is rather strongly biased against those type of organisms that lived in shallow water, highly oxygenated shelves. So we might be missing part of the story here. However, in the context of North Greenland, we should keep in mind that we're not strictly speaking at lateral equivalents, because the Sirius placet Lagerstätten is slightly older than our SCF assemblage. So the difference might as well be tenfold. Also, what we should keep in mind is that this line does not only represent a fascist transition, it's also a front of deformation. So all the carbonaceous material that is occurring above this line has likely been volatile. So all of the fine features that you can see on these sepal arrays, as well as these pterobrans, these phylogenetically significant features are likely to have been removed above this line. So there's likely to be quite a strong taxonomic bias on this signal at the moment. So to conclude on this, we have identified quite important taxonomic differences between soft-bodied biotas from the Sirius placet Lagerstätten and the shallower water SCF assemblages from southern outcrops. But the exact contribution of taxonomic, temporal, and spatial constraints on this signal at the moment is a bit unclear, especially because of the complexity of the North Greenland setting. But the sheer preservation of exquisitely preserved SCFs in shelf environments still demonstrate that they have a capacity to resolve paleoecological trends beyond the Burgess Shale type taxonomic window, which is confined to these deep water environments. And with this, I thank you very much for your attention. Thank you, my supervisor as well, which have been very helpful. And I'm going to share also a link for this study if you want to know more about this. It's been released just a few days ago.
Thank you so much, Elise, for a wonderful talk. And we've got plenty of time for questions. So if you have any questions, do pop them in the chat. And I think Elise is going to pop a link. There we go. There's a link in the chat as well if you want to know more. Javier has a question. Is there a chance that those cetal assemblages might be the X-pods of the Waptid Pauloterminus for Sirius placet? And then asks, Waptia for Burgess Shale has quite feathery exopods posteriorly. If I pronounced any of that incorrectly, it's written down in the chat, and apologies. What do you think, Elise, to that question?
Well, it's a difficult question. It's kind of hard to compare Burgess Shale type macrofossils with SCFs because they don't have the same level of detail. So the most obvious comparison that I found to my assemblage here were obviously other SCFs from the Marquette Formation, but also the early formation. Now, we cannot fully exclude the possibility that it comes from something else, but it's pretty unlikely. So far, the very finely denticulate leading edge that we find in those crustacean mandibles are quite diagnostic of crustaceans.
And we have a question from Lucy, who says, a brilliant talk. And are you seeing any cyanobacterial tubes or other similar things which you might expect in the photic zones?
We did recover a lot of cyanobacterial tubes, indeed, but not in all samples, intriguingly. There was, all the samples have been recovered from a meter-thick interval, and I've recovered a lot of cyanobacterial tubes in one of them. So it seems to be quite a patchy distribution.
Excellent. Thank you once more for a wonderful talk and the answers to those questions. If you have any continuing questions for Elise, please do keep them coming in the chat, or maybe you will digitally bump into her in the Discord server where you can ask more questions. At that point, we are going to move on to our final speaker of this session, who is Nydia. Are you joining us today, Nydia? Are you there?
Yeah.
Wonderful. Hello. And we can hear you loud and clear, which is brilliant. And so we're going to call up your slides. There we go.
Okay.
Thank you very much. Take it away.
Thank you. Oh, well, hello. So today I'm going to present our interpretations for the internal anatomy of this blastoid. So for those who doesn't know, blastoids are an extinct group of echinoderms which superficially looked a lot like cranids. They possess a root system for attachment to the substrate, a stem to keep a well-sutured body above the sediment-water interface, and arm-like structures which function in feeding. So blastoids are found globally in a variety of environmental conditions, and they range from the Silurian to the end of the Permian, period through which they became important components of marine ecosystems. We just have to be careful with comparing cranids and blastoids because anatomical comparisons are sometimes a bit dangerous. So their bodies are composed by up to 1 million skeletal elements, but usually only about 20 are found. The good thing is that these elements form a stable body plan, so it can be or is widely used for taxonomical identification. So the object of our study was a little blastoid called Hyperoblastus reimanni from the Middle Devonian of the Silica Shale Formation, and is kept in the Cincinnati Museum Center. We came across this scan in late September for an unrelated paper, and we quickly realized that it had some very interesting structures internally that needed to be further analyzed. So unfortunately, the arboreal side of the specimen is not nicely preserved at all, so we can't really see any of the deltoid or radial plates. For that reason, we were forced to find homologous specimens for size comparison of body and body opening dimensions. And these two homologous specimens we found are from the University of Michigan Museum of Paleontology. So now if we could please see a video that I have prepared. Okay, here we go. It's already started. Okay, let's see. There you go. So the arboreal surface is not nicely preserved, as I said, but the basal one, it is, and we can actually see well-sutured plates there in the bottom. The internal cavity is occupied by 5 vertical structures, which are identified to be the hydrospires. In the basal part, we can see a coiled structure, which is identified to be the coelomic system. And this system covers the rest of the organs found internally in the body of this blastoid. So if we come back arborally and beyond the hydrospires, we can see that there are 4 vertical tubes right there, which are crowned by a suspenterradial structure, which is identified to be the peristomal ring with associations to the nervous and the hydrovascular system. So coming back down and looking at the 4 vertical tubes, We have identified the two in the middle are the gut, and the two lateral tubes are probably the humal and axial system. The mouth of the specimen is found centrally, and it gives way to the esophagus, which bends basally and comes back abruptly to disembogue into the anal deltoid and the anal opening. So right now we're looking at the anal opening. Underlying the central gut, we can see a symmetrical structure right now in purple, which is covered by the coelomic system and the hydrospires, well tagged in the middle and protected. So if we look closely, we can actually identify further 5 structures inside of this cavity, which are right there. So the first 3 are the smallest ones. They're very close together, and they're ice cream cone shape. They are located right below the anal deltoid, on the part of the gut which goes to the anal opening. This is the third structure. The next structure is the largest, highlighted in purple right now, and it's located in between the buccal and the anal openings. And the last structure seems to be connected to esophagus through a white tube. So those are all the structures we identified inside of the blastoid. So we'll come back to the slides, please. Okay, there you go. So from that reconstruction, we created a model of the internal anatomy of the blastoid. Now, for time constraints, I know I'm talking very fast, but I don't have time. So for time constraints, I will only be talking about some of those organs. And the rest of the organs, you'll have to read the paper if you want to see about them. So hydrospires are ubiquitous structures in fossil blastoids. They're very commonly found. They are arranged as 5-pair subpentaradial fashion. They're actually bilaterally symmetrical. And they are calcite folds that are hanging from the inside of the ambulacral, of the ambulacras, inside of the cavity, the central cavity. In this case, there seems to be a reduction of the hydrospires in the mid picture, but this is just a diagenetic artifact, which can also be seen in a displacement of the coelomic system right below. And in addition, other descriptions of Hyperoblastus reimanni did not find a reduction of the hydrospires in any of the specimens analyzed. Okay. Next one. Okay, so the coelomic system occupies the majority of the basal part of the body. It's a coiled structure which is separated by a vertical membrane into 2 interconnected compartments in its basal part. The abral part, there seems to be some preserved bits of this system, but did not allow for the completion of a reconstruction. So this system is similar in shape and morphology to those coelomic systems described in cranids. Well, I keep pressing. There you go. Okay, so the gut is a well-defined, simple U shape, which sits centrally in the body and is covered by the perigastric coelom, as seen here in the picture. So the perigastric coelom is an extension of the middle membrane that separates the coelomic system into 2 basally, as I was saying before. So guts in blastoids are not very well known because there is not many at all. In 2015, Rahman et al. Described a gut in a larvae Petroblastus, and the gut was similar in shape and morphology to the one described here. So then centrally in the base of the hydrospires, we have a chamber which we identified as interpret as the brooding chamber. So other reproductive systems described in other specimens of blastoids have been always located in the interanal area, right below the anal deltoid. And the gonad usually connects to the exterior through a gonadote, which disembogues either through a special opening called the gonopore, or just directly into the anal opening. So inside of this structure, we can see another 5 structures. The first 3 are the cone-shaped structures, and we identify those as cystidian stage larvae. The next structure, which is the largest one in blue, is identified as a gonad. And the last structure in gray, which is in the opposite side of the body to the anal opening, remains unidentified. Okay, so the dimensions of the cystidian stage larvae, or the juveniles, the brooding juveniles, are very similar to those dimensions given by Sebastopoulou 2005. So juvenile number 2 in the center is the worst preserved, and this reconstruction probably shows some diagenetic artifacts that are masking the original morphology of the juvenile. Juvenile number 1 is the best preserved, and it can be clearly seen by the cone shape. So previous descriptions of brooding in blastoids, because this is not the first description of brooding, talked about the eggs which were hosted in the anal hydrospires. The anal hydrospires were greatly reduced. This description was done in Penthremites rusticus. The anal hydrospires were greatly reduced, and hundreds of eggs were hosted there. In modern echinoderms, we can see brooding behaviors across 4 of the 5 taxa, groups. So when this happens, sometimes we can see that there are chambers, special chambers inside the mother's body where the juveniles are brooded. In the case of crinoids, for example, we can see this type of behavior where juveniles up to pentacrinoid stage larvae are brooded before let out into the environment. In terms of exiting the body, the dimensions of our juveniles, or putative juveniles, are 0.6 millimeters in height and up to 0.5 millimeters in diameter. Now, a gonopore has been described in a specimen of Hyperoblastus phylosus, which is comparable to our specimen. This gonopore was pretty small, measuring about 0.3 millimeters in diameter. But in another specimens of blastoids, larger gonopores have been found, measuring up to 0.5 millimeters in diameter. So here we hypothesize that the specimen of Hyperoblastus phylosus was a male, and so the gonopore was smaller. And in females, the exiting of the body is achieved either through larger gonopores, which haven't been identified, or directly through the anal opening. So, as I said, the abdominal surface is not very well preserved, but we calculated how large the anal opening for this specimen would be. So the estimated size is between 0.66 and 0.67 millimeters in diameter, which is large enough for all the brooded juveniles to exit. Okay, so the next, the gonad, the largest structure here on the top, is longitudinal and has a bulbous texture. So the bulbous protuberances are similar in morphology and size to those eggs described in Penthremites. So the Penthremites eggs had an average diameter of 0.16 millimeters. Our putative eggs have an average size of 0.20 millimeters. Okay, so the coelomic system encloses all major internal organs, and this is the first record of any fossil blastoid with a coelomic system extending below the basal boundary of the gut. So gonads and eggs have been described in various species of vesiculate blastoids. Hyperoblastus is classified as a vesiculate, however, relocated later on to spiraculates. So Spiraculata is believed to be a polyphyletic group. Therefore, the appearance and positioning of the internal brooding chamber might be a reflection of their divergent tendency. Sexual dimorphism, possibly internal fertilization, must be developed in blastoid species with advanced internal brooding. Various types of parental care are well documented in modern echinoderms. These are very common in environments with inhospitable conditions and high risk of predation. Matrotrophy has been observed in many cases, and when this occurs, the overlapping of successive generations of young being brooded concurrently is common. This fossilized evidence of internal brooding of juveniles in blastoids is one of the earliest indication of brooding in the fossil record of the Echinoderms. And now, just to finish, we all know how powerful synchrotron tomography is, but now it's been proven to be a powerful tool for non-destructive reconstructions of exceptionally preserved internal organs in fossil specimens. So with all that, I'd just like to thank my co-authors and Johnny Waters for a very, very useful discussion. Thank you.
Excellent, excellent. Thank you very much. And we've got time for a quick question from Jeffrey Thompson, who asks, what are the phylogenetic relationships of this blastoid to the one described by Rahman et al. In 2015? And what does that imply about the phylogenetic distribution of U-shaped guts in blastoids?
Well, now, thanks, Jeff. My knowledge of blastoids goes all the way back to about 2 weeks. So I don't know that much about the phylogenetic relationships. Now, the interesting thing about the gut is that the blastoid that was described in Rahman et al. 2015 was a larval stage blastoid, and in our blastoid is a fully adult because it has it's actually brooding babies inside it. So that shows that the ontogeny does not change the shape of the gut. And that's probably as much as I can say there.
Excellent. Thank you so much. And thank you once more to all the speakers in this first session of this year's virtual annual meeting. I'm very grateful for some brilliant talks, which were both superb in style, substance, and importantly, for your chairs, keeping to time. So future speakers look towards those in this session as perfect examples. Just before we leave this session, a few reminders. Session 2 is starting in 15 minutes, chaired by my wonderful colleague, Ricardo. So you will need to use the separate link, go back to your emails and use the link for session 2 to get into that one. And then after session 2, we have the poster session. All the posters are online on the Palace website for you to peruse at your pleasure. But on the Discord channel, you can meet with the poster presenters in both voice and video and written chat as well, and discuss your thoughts, ask them questions and get the answers you need. And then at lunchtime UK time, we have our first field trip, Edward Fluid, and the first fossil field guide. We welcome you to our lovely collections. You can see T-Rex hiding in the background there, and the public are in having a look. Thank you so much for joining us, the hundreds of you who were up this morning to join us, and see you in just under 15 minutes for session 2 of this year's Palace annual meeting. See you soon.